Hello. So right now I'm going to talk a bit about the second law of thermodynamics, or entropy in this case. This is a really important topic in physics within statistical mechanics. In fact, I remember even hearing a joke in physics, I guess, or diagram from a famous physicist, where he essentially said that if your law does not work with entropy, then the whatever you just made does not work in general. Entropy is a super important concept, is also a statistical law, aka means that it's more likely to happen than not. And I'll talk a little bit more about this today, and I will probably even expand on this in the future. But right now, keeping with entropy, like the definition, is the amount of disorder in a system, or uncertainty. You could even say randomness to a degree as well. Random. In a system. Entropy is also related to some other useful or interesting topics, which I recommend checking out. Information theory is quite interesting. If you're interested in that, I suggest checking it out. Anyhow, entropy, given by the variable S, or big S, this is entropy. It is in units of joules per Kelvin. So in terms of like the dimensional analysis, joules, of course, being broken up is energy, and that is second squared over Kelvin. And a bit more on entropy, it's also how much useful work, like the amount of like useful or unuseful work, I should say. Such unuseful work, or W, in a system. A good example of this would be like fossil fuels. Fossil fuels have a low entropy, as in they provide low entropy, as in they provide more useful work. So in that case, it could be considered it's more ordered in a way. So that way it can produce something that it can reduce the entropy of something else, because overall, we'll talk about this before, but entropy is generally increases, or it's likely to increase, as is a statistical law, which we will talk more about, especially in future videos, because it's really, entropy is such a really phenomenally interesting topic. But low S, so for example, if you were to put in like liquid gas into like your car right here, it then goes into the car. It's then used, I don't know, the engineering components of a car, like works the engine, so on and so forth. But the input would be like liquid gas, and then output, or some of the output that's not used within the system itself, would be, for example, like the exhaust from the car. So this exhaust from the car, so as stated within the first law of thermodynamics, which is just energy conservation, right? Just this law, like Q is equal to change of U minus P dV. Another way to write it, like this law in general, all the energy within this system from input to output stays the same. However, we can't just collect all that exhaust from a car. By the way, please do not do that. Please do not. From a car, and then put it back in, and then the car can work again. Why? It's because even though the energy remains the same, the energy that came out of this system after being used is less useful or provides less work, is higher entropy from the system as the entropy increased from this system. Another interesting thing to talk about, and this also goes with the liquid gas being put into a car, and then some of the output being petroleum, but this concept of the arrow of time for like entropy, or like entropy help explains like a temporal order in a way. And that is like, for example, if we break a glass, like we shatter it, it's shattered, so we have at one point, so at T1, for example, we have glass, which I will just make like this, glass, and then at T2, it then is shattered. So we have, glass broken up. Can those pieces, do you normally find those pieces reconvening back together to then go back to T1? No, you normally don't. If someone like jumps into a pool, you don't normally see them jumping out of the pool as in like a reversible process. This might seem obvious, but from all laws that we have in physics, like for example, the Newtonian laws, it doesn't say that it is permissible for a ball to go back, in a sense. That's a weird topic. I might explain that more in the future, but overall, the system in of itself increased in entropy is now less useful. This also explains, as I said before, the arrow of time. So why are these events not reversible? Entropy. So it is irreversible. We'll talk maybe about some more reversible systems a bit, but overall, things are normally irreversible, or the reversibility is idealized. So, overall law, entropy increases generally, or entropy increases. You'll see this inequality quite a bit. Overall, entropy increases. You will also see that, for example, change of entropy is equal to change of heat over temperature, which of course can also just be change of U minus the work, that's volume, over temperature. And we can also see that this temperature right here, joules per Kelvin. Since this top part, the heat, is the energy, bottom part, temperature, is measured in Kelvin. And this will also go into this idea, or into the concept of temperature, which we'll talk a little bit more about, being the change of energy with respect to entropy. Anyhow, thank you so much. Let me know if I made a mistake. This is a concept that I will talk more about in the future, as entropy is such a useful concept in physics. But anyhow, thank you again. I hope this helped, and I hope you are having a wonderful day.